So we've already talked about series DC circuits, and now we're going to talk about parallel, which is another configuration you're going to see a good bit. So let's discuss what we're going to learn in this section. We're going to talk about the characteristics of a parallel network and how to solve for voltage, current, and power to each element, just like we did for series. We're also going to develop a clear understanding of Kirchhoff's current law. Yes, Kirchhoff has a current law in addition to his voltage law, and it's important to the analysis of electric circuits. We're also going to talk about how the current will split between parallel elements. So parallel resistors divide the current just like series resistors divide the voltage, and we're going to apply the current divider rule. We're also going to talk about open and short circuits in this section, and we're going to talk more about how to use an ohmmeter, voltmeter, and ammeter in measuring parallel elements. Okay, so two network configurations, series and parallel, form the framework for some of the more complex circuits you're going to look at. And it's really important that you understand series and parallel and how to decide whether components are in series or in parallel, or if they're in neither. You will find that. So in geometry, you're used to seeing parallel elements as, for instance, two straight lines that don't intersect, right? That's what you're used to seeing in as far as parallel. And I want you to get that image out of your head because it really doesn't apply in circuit analysis. Parallel actually is when we have two elements or branches or circuits that have 2 points in common. That's going to be the main way you tell if you have a parallel connection between your elements. So what do we mean by that? Well, in this case, we have R1 and R2 in that circuit A, and you see that they're connected on this side, and you see that they're connected on this side. So those are in parallel because they have 1, 2 points connected between them. Okay, so for the second one, R1 is connected to R2 over here, and R1 is connected to R2 over here. So that's 1 connection, 2 connections, so they are in parallel. Okay. If we combined R1 and R2, that would be in series with R3, but we'll get to that probably next week. Okay. So in part 3, notice here, or C, I guess, R1 is connected to R3, R2 is connected to R3 here, but R1 isn't connected to R3 on both sides, and R2 isn't connected to R3 on both sides, only on one side each. Now, if we combined R1 and R2 in series, and we know how to do that, we would just add them. The combination of R1 and R2 would be in parallel with R3. Okay, but again, that we'll get to later on in our course. Okay, some other configurations or how parallel resistors might be drawn. Again, try to avoid looking at these as if they are geometrically parallel. It really doesn't matter. The only thing that does matter is that they're connected here and here, so all 3 of these resistors would be in parallel, or that they're connected here and here, so all 3 of those are also in parallel, or if they're connected like this. Okay, so again, it's not that they're drawn so that they look parallel, it's that they have those 2 points in common. That's extremely important. So let's look at a circuit that's a little more complicated, and let's try to determine all of the connections between the resistors in this case. So I'm going to start with the orange over here, and R1 is connected on this side to R3, to R4, and to R2. Okay, those are all the connections right there without going, we're not crossing over a resistor, we're only showing the connection to each end of the resistor. And then the connections between R3 and R4 and R5 and R6 over here. Okay. And then let's look at the connections elsewhere. Okay, so R6 is connected over here. Where's it going? It's going to R5, it's going to R2, and it's going to our source over here. Okay, and then let's use our green. From R1 we're connected up to the voltage source. Now, the easiest way, once you get this drawn, if you want to use your like colored pencils or colored markers or whatever, the easiest thing now is to look for resistors that have one color on one side and the same color on the other side. So here, as you can see, R3 and R4 have that orange side, and they also have this blue side. So that means that R3 and R4 are in parallel. So I use these double lines to indicate that they're in parallel with each other. Okay, parallel. That's kind of my shorthand for writing parallel. All right, what else do we see? Well, R1 and R2 have an orange end as well, but notice R1 has green over here, R2 has red, so they are not in parallel. Okay, a lot of folks think that R2 and R5 would be in parallel. So let's look at that. They do share this red end over here. Let me get rid of this here. They do share that red end, but they've got R2 has an orange side and a blue side, so they're not in parallel. Okay, they look parallel because of the way they're drawn, but they are not electrically speaking in parallel. Okay, and then let's look at R5 and R6. So R5 and R6 share a blue side here, and they also, look at there, share a red side. So R5 is also in parallel with R6. Okay, and I believe that's everything. And that's it. So R5 and R6 and R3 and R4 are in parallel. Now notice over here, I'm going to use that green right here, that there's one connection between the source voltage and the resistor R1, and there's no other path for current between them. So E and R1 are in series with each other. So start trying to pick up on those relationships while you're working through these circuits, and see if you can tell what's in series and what's in parallel. Now remember, in series we could add our resistors together. In parallel, we're actually adding the inverses of our resistors together to get the inverse of the total resistance. So what do I mean by that? I mean that 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 for parallel resistors. Because when we add resistors in parallel, we actually end up decreasing the total resistance of the circuit, whereas with series resistors, as we add resistance, we're increasing the resistance, right? This is just a difference in how the parallel circuit works. We're dividing down that current for every resistor, and we're actually we're dividing that current into different portions for the parallel resistors, so that actually increases the total current of the circuit, or the current required of that source, and that's why we're actually decreasing the resistance as we add resistors in parallel. So when I said the inverse of resistance, that actually has a name. The inverse of resistance is called conductance. Okay, so resistance resists the flow of current, conductance encourages the flow of current, if you want to think of it that way, and we call that G. Okay, it's given its own symbol, which is 1 over R. So the total conductance of a circuit would be 1 over RT. The conductance of a particular resistor would be G1 equals 1 over R1, and so on. So if you want to think of it this way, in parallel, we're actually summing the conductances instead of the resistances. Okay, so I'll show you how to do that. In general, we use this format. So remember, we said 1 over RT is 1 over R1 plus 1 over R2 plus, and and so on until you get until you account for all of your resistors in parallel. So if we invert the whole thing so that we have RT right here, it looks like 1 over and then the rest of this in the denominator. Okay, so let's actually calculate a few of these and see what we get. Let me see. All right, so we have, next circuit. Let's calculate our total resistance here for this circuit. So RT is going to be 1 over 2 plus 1 over 200 plus 1 over 1K, which remember 1K is 1,000, so when you put this into your calculator, make sure you remember that. So when I put this into my calculator, here's kind of what I do. I'll take the 2 and I'll raise it to the -1 power. Okay, 2 to the -1 is 1 over 2. Okay, and you might have, like, in order to do this, you might have an x to the -1 button like I have. You might actually have to use this this exponent button and then type in the negative and 1 after it. And then I will add the next one, so 200 raised to the -1 plus 1,000 raised to the -1, and then I hit enter. And here's really important because right now we've only done the denominator, we haven't done the top yet, so we have to invert it again at the end. So after I hit enter, then I hit my x to the -1 button again, or raise the whole thing to the -1 to get my answer. Okay, and when I do that, I get 1.98 ohms. So notice something. The original values of resistors I started with were 2 ohms, 200 ohms, and 1,000 ohms, but the final total resistance of the entire network of resistors is 1.98 ohms. It's actually less than my 2 ohm resistor right here. So what you'll find is, in parallel, RT is always going to be less than whatever your smallest resistor is in your circuit. And that's one good check that you can use when you're working through these. If I had come up with a number that was 20 ohms, I would know that's wrong because it has to be less than the smallest resistor in my circuit. Okay, let's try to find the total resistance for this group of resistors here. So again, RT is 1 over 100 plus 1 over 1,000 plus 1 over 10,000. So when we plug this into our calculator and practice with this a little bit, we get 90.09 ohms. Again, that is less than my smallest resistor here. So which resistor do you think has the biggest impact on the total resistance of your circuit? Actually, it's the smallest resistor. Remember when we looked at series resistors, the largest resistor had the biggest impact on the resistance of the circuit. Well, for parallel resistors, that's actually the opposite. The smallest resistor is the one that has the largest impact on how that circuit works, because that really determines how much current we're going to pull from our source. Okay, so let's do a slightly larger one now, we've got, let's see, 6 resistors here. So we could use this same equation, 1 over, and then we've got 22, 10, 22, 10, 22, and 22. So once you plug all of that into your calculator, you get 2.62 ohms. And we might come back and revisit that one in just a moment. Let's try one more case here where we have 2 parallel resistors. Okay, so remember, when I say special case, I mean that you can use this, but only if certain conditions exist. And this is only good when you have 2 parallel resistors in your circuit. All right. So when you have 2 parallel resistors, you can do something we call product over the sums. Okay. So what do I mean by that? I mean that RT will be R1 times R2 over R1 plus R2. Now, if you have just 2 resistors in your circuit, this might be a little bit quicker for you. So we're saying 0.8 times 5 over 0.8 plus 5 will give you RT. So what is that? Let's see, this problem is not on my paper here, so 0.8 times 5 is 4 over 5.8, and that is 0.69. Now again, is that correct? Well, it has to be smaller than 0.8, so that's a good sign right there. You could also check this. You could just go back and do this the original way, 1 over 0.8 plus 1 over 5, and see what you get there. 0.8, 5, and I get the same thing, 0.69 ohms. Now this equation here, this always works. Okay? This always works. This right here, this equation, is only for 2 branches or 2 resistors in parallel. Okay? Only for 2. All right, so let's work on applying this to some circuits in our next video.